How to draw a force diagram. It's a 5-step process. Here we go. Step 1, identify the object. What is it that you want to draw a force diagram for? In this, let's go through this in the context of a problem here. So we got a man pushes with 300 newtons of force, that's like 75 pounds, on a 200 kilogram crate that remains stationary on a truck. Okay, so we got a crate, we got a truck, we got a person. Which one of these are we going to draw a force diagram for? I'm going to say the crate. Okay, so let's say that's done. It's going to be for the crate. Now, step 2, do a force inventory. This is going to be like the assignment I just asked you to do. So, well, I'm not done with it. Let's do that, though, right here, right now. Force inventory. Okay, you don't have to do it exactly like this, but I want you to identify the following things. What are the meaningful forces acting on this crate? Well, the one that I'm always going to pick when we're on the planet Earth is gravity. And then I want you to identify, just like in that homework assignment, what is the thing exerting this gravity force? That's going to be the Earth. Then, is there a way that we can quantify, come up with the size of this gravity force pulling down on the crate? And there is, because I'll just put it over here. The weight of this object is going to be its mass times 10 newtons per kilogram. So what is its mass? It's given in the problem, 200 kilograms. And then we multiply that by 10 newtons of gravity force for every kilogram of mass, and that's going to be 2,000 newtons. Okay, so what is that in pounds? That's going to be like 400 pounds. So, since I have a formula that allows me to know it, like it's not given in the problem, but I got this easy formula to use it, I can write that down. So here's the size of the force. It's going to be the gravity force on the crate is going to be 2,000 newtons. And the direction, the last thing I want to do is down. Okay, now, what's another force that I know? I know that the crate is not falling, so that means the truck is pushing up. That's a normal force. Remember, normal is a weird name for a very typical force, pushing. It's going to be the truck or the trailer. I'm just going to write truck. Okay, now, right now there's nothing in the problem to say what size that force is. So I don't have a formula. I mean, we're going to be able to figure it out pretty easily after we do our force diagram, but I'm going to say right now, I don't know what that is, so I'm going to leave it blank, but I know that it's up. All right, so that takes care of the up and down forces. Gravity down, truck pushing up with a normal force. Okay, then I got this guy pushing on the crate. Pushing, that sounds like a normal force. Again, normal, weird name for just a typical, anytime push. All right, it's going to be the man, the person, the human. Okay, now this one, I'm actually given the size of the force. 300 newtons, I think I said it's like 75 pounds. And, can I tell which way he's pushing? Yeah, he's pushing to the left. I like to use arrows instead of words for direction. Okay, now, the crate remains stationary. But I thought forces cause acceleration. This guy's pushing. Well, there must be some other force that's kind of pushing back, resisting, and that is friction. So even though we don't see anything between the crate, the bottom of the crate, and the truck top, there's going to be friction. How do I know that? Because he's pushing and it's not going anywhere. All right, so that's going to be a friction force. Now, what's exerting that friction force? The truck again. You could say trailer if you want. Okay, now, I don't know what size it is, so I'm going to leave it blank. We're going to know pretty soon, but I don't know right now. But I know that if the man is pushing to the left and that crate's not going anywhere, that's got to be, the friction force has to be to the right. Okay, so this is our force inventory. I think there's 4 forces. Now, let me talk about forces that aren't very important. Okay, so this crate is in air, and we're not used to thinking of this, but the air around the crate creates an upward buoyancy force. Like, it's the force that why we see a helium balloon going up in the air. But that force is tiny compared to gravity and the normal force up, so I'm going to ignore it. There's a gravity force between the crate and the truck, and the truck and the crate. It's real, it exists, but it's too tiny to worry about. So these are the 4 big or meaningful forces that actually matter when it comes to predicting what's going to happen to this crate or understanding what's happening to this crate. All right, so there's our force inventory. Number 3, represent your object as a dot. Now, you could just draw a little box down here if you want, but I'm just going to do it kind of the way it says. So I'm going to represent the object with a dot. So the dot I just drew is the crate. If you want to draw a little box that looks more like the crate, that's fine too. That was fast. Done. Okay, the next one. Draw arrows to show the known forces. Bigger forces mean longer arrows. Label the arrows size and type of force with the size of the force and the type of the force. Okay, so arrows do a fantastic job of showing on paper what we can't see with our own eyes, which are forces. Big arrows are big forces, and the direction, little arrows are for little forces, and everything in between. And the direction of the arrow, of course, is the direction of the force. All right, so I'm going to draw gravity. Well, let's go right through them. I'm going to draw these. I'm going to draw the ones that I know the size of. Okay, so gravity, 2,000 newtons. So I'm going to make a nice red arrow for that. Now, I draw it so that the arrow starts at the dot and goes down, and of course it's going to go in the direction of gravity, which is down, and there you go. Now, why did I draw it that long? Could I have drawn it longer? Sure. It's just a scale. It's just like this represents 2,000 newtons of force. Now, I'm going to label it with the type of force. I'm not going to take the time to go through that here, but there are, I'll just say it in the Nearpod that there is the list of symbols. And it turns out we're going to use W for gravity. You say, why not G for gravity? Well, if you really want to use G, that's fine. But I want you to think about weight is gravity, weight is gravity. So there, all right, so anyway, W for weight, which is gravity. All right, and then in parentheses, I put the size of the force because it's listed, or actually we calculated it, 2,000 newtons. That's going to help us figure out unknown forces. Now, the other known force I see is I know the size of the pushing force of the man. I'll just use blue for that one. Now, this is not that important really, but we always, okay, so this is what I don't want you to do, although it's not a big deal. And again, it's not a big deal. If you want to do it this way, actually, that's fine. But we don't draw our arrows like this. We draw them so that the tail of the arrow is always touching. So in other words, I'm going to draw the guy's push like this. And then that's a pushing force. And so that's a normal force. And since it's listed, where is it? It's 300 newtons. That's around 75 pounds. So he's pushing pretty hard. Okay, now, those are the only 2 forces I know. So, I'm done with step 4. Now, step 5. Use Newton's first law and second law, really should be second law, to figure out any missing force values. What? Well, this is where we're going to deal with the normal force of the truck pushing up and the friction force. Now, I know that the normal force of the truck is pushing up. And I'm just going to make that a green arrow. So I know it's going to be like this, but how long do I make it? How much force? And this is where I look at what is the acceleration of the crate. The acceleration of the crate is 0. It is not accelerating. It's not speeding up. That means Newton's first law says no acceleration means the net force must be zero. Remember, net force is the sum of forces, so I need as much up force as I have down. So I'm going to draw this green arrow, try to make it exactly the same. It's not going to be exactly the same length, but I'm going to try. And I'm going to get rid of that little question mark now because I know the size of this force. So this is the normal force of, whoa, come back. This is the normal force of the truck. And I know that it's 2,000 newtons. It wasn't given to me in the problem, but I need as much up force as I have down force. Oh, I forgot to add. I should add a little earth here, and I should add a little man here, or human, or person, or whatever you want to call it. That creature. Okay, now there's one more known force, but I think you're going to see that that's not trucker. It's a truck. All right, whatever. Let me just finish. Wasting time. Truck, not trucker. Trucker is the nickname of somebody who drives a truck, but it doesn't look like truck, but you get, oh, whatever. You know, that's truck. Okay, it's truck. All right, so I know the friction force is going to be pointing to the right. So we're going to do pink or purple, whatever you want to call it. So I know it's going like this, but how much force? Well, again, let's look at the acceleration of the crate. It's not going anywhere. So the acceleration is 0, which means you need, when we add up all the forces left and right, they have to add up to 0. So if I've got this guy pushing to the left with 300 newtons, I need just as much friction force. So that's what I'm going to do. I'm going to make that arrow just as long. I know what it is now because Newton's first law. And I'm going to label it. Okay, this one, I just use a little cursive F, kind of a little italics F. And that's going to be the truck. And I know that it's going to be 300 newtons. And we are done. So I could, using this force diagram, you could ask me anything you wanted to know about this. And you'd say, well, what's the friction force? 300 newtons to the right. How hard is the truck pushing up? 2,000 newtons, about, what did I say? That's around 400 pounds, something like that. So these two forces were essentially almost given. This one was definitely given. This one was easily calculated here. But the normal force of the truck up and the friction force, drawing this force diagram kind of made it easy, hopefully, to know what those two forces are. Anyway, that's how you do it. I'm going to show a couple more examples that are a little more complicated that involve a monkey rule and an elephant rule in the next video. But this is a good start.